Hi Chandler, I thought it might be easier if I did it like this. That way I can draw problems and show examples. Okay, population is everybody. Like all the US or something like that. It's everybody they're talking about. Something like all the people in the US. Whatever the giant group is. And then the sample is like randomly taking some of those. So like maybe you randomly took 30 people for your study. A group of 30, for example. Okay, a statistic, this is like the standard deviation, the average, the average, the median, the 5-number summary, the range, all that kind of stuff of the sample. So they both start with an S, so that's nice. This is the standard deviation. This is the one on the calculator that is the S. That's the standard deviation of the sample. Okay, so statistics are all of that stuff for the small group. A parameter is all of that stuff for the gigantic group. So that's all the same stuff. That's the standard deviation, the average, the range, all of that stuff for everybody. Okay, and the standard deviation for that on the calculator was that Greek thing. Okay, so like think about 360 million people in the US and then you pull out like 30 of them for your sample. So these are called that's the average. So you see you have the average. This average is close to this one, but they might not be exactly the same. You might accidentally have gotten some extra tall people. And the standard deviation of the sample. The spread here might not be quite as wide as the spread there. And the 5-number summary might be different than it is up there. And then if you got another sample of a different 30, they might be a little bit different. See, so each sample has like its own personality. Okay, descriptive statistics. I'm not sure. Just look what look up what those actually mean. I'm not completely sure. I do have one for discrete variable though. A discrete variable means it comes in chunks. Like, I don't know, maybe they're doing how much homework you do by the half hour, or like when you go to work and clock in, it comes in chunks of 15 minutes. There's no such thing as every infinity second. And then continuous means it could be 1, it could be 1.1, it could be 1.2, 1.3, 1.4. So continuous, it's smooth data. Bias is like maybe people have an opinion already, so they don't really, so they even unintentionally make the data a little bit different. Like a radio show that wants to talk about gun control, well, that would be biased data because only people call in that have a real opinion about gun control. You're only going to get the two extremes, people who want guns and people who don't want guns. Most of the middle doesn't show up. Distributions. So uniform distribution is kind of like the normal bell curve. So you have high, medium, lows. Left skewed. Let's see. Left skewed is like that, where the bump is on the right side. So I always tell my kids it's like you're skiing. If you're skiing down this hill, you ski to the left, right skewed, is like this. It's where the tail is. It's where the extra tail is. Normal, symmetric, or bell-shaped. Oh wait, that's this one up here, this picture. Uniform is where they're basically all the same. Most everybody is this, almost all the same. Uniform, same. Normal is bell-shaped and symmetric. Resistant data are those things that don't change if you make a mistake. Like, let's say you have a test score of a 90 and a 80 and a 85. So we can already tell the average is 85. Okay, so we could get the average. That would be 85. We could get the standard deviation. So see, the spread's not very much. So standard deviation's not that wide. The range is from 80 to 90, so that's 10. So both of these are spread kind of numbers. So if the range moves a lot, the standard deviation will move a lot. The median, that's the middle score. So the middle score of this would be 85. Okay, let's just say that we throw in an extreme value. So let's say I throw in another value that is extreme, like 1,000. Okay, see how we took the average now. The new average is going to be, if we add it all up and divide it by 4, it's going to be like 400. See, the average moved, not resistant. Resistant means it resists change. The standard deviation. Okay, standard deviation has to do with spread. The spread was 10, now the spread is like 1,000, so the standard deviation is going to be much bigger, not resistant. The range went from, it was 80 to 90, so it was 10, now it's 80 to 1,000, so now it's like 920, not resistant. So you can just make up a little case like that and see if it resists change. Median is middle. Okay, if we put these in order, I'll put the 85 here and the 80 there. See, before, that was the middle one. Well, now what's the middle one? 1, 2, and then 1, 2. So now the middle is right in there at about 88. See, it didn't change very much because the median is resistant. It resists change. Okay, I think they have a practice for all of these, so let's take a look at what they all are. Remember, a frequency distribution is just okay. How many people are aged 1 to 10? 20 people. How many are 11 to 20? 30 people. That's frequency distribution, where maybe this is age, and this is how many. Okay, and then relative means turn it into a percent. So then you just make another one. You figure out how much they are. Let's just say 21 to 30 is 50. So now we got 100. So relative is 20 out of 100. So that would be 20%. 30 out of 100, 30%. 50 out of 100, 50%. Okay, that's all relative means. Side-by-side bar graph, a pie chart, a histogram, a stem and leaf plot. If it was, well, I think they probably have a question like that, so we'll just do that. Okay. Dot plots, figure out why a graph is deceptive. Okay, I think you probably have most of these. Percentiles are percent below. So if you have some numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the 25th percentile is talking about right there, because that's about 25% are below. The 75th percentile, 75% below. So if you're in the 90th percentile, you're way up here, 90% scores are below. Remember what a z-score is? It's so a z-score is like this. It's when you have a standard deviation. Let's say the average of some population is 100 with a standard deviation is 10. Okay, so the middle would be 100. And let's say it's normal. So one step up would be 110 and one step down would be 90. Okay, that a z-score, 0 is always average. So for a z-score, that means that number is 0, one step up and one step down. On the standard deviation of 10, 120 would be the next one up and 80 would be the next one down. That's 2 z-scores and that's -2. And then 130 would be the next one up and 130. That's 3 z-scores and -3. So that's the concept. That's 68% of the people are usually in there. Another 13.5 are in there. And then 2.5 are out there. About 2.5. That adds up to this. This is how you remember it. Up and down 1 holds 68%. Up and down 2, see if we do 68 plus 13.5, 13.5, that's 95% of all scores. And up and down 3, that's 99.7%. That's called the empirical rule. 68, 95, 99, 7. So you want to remember that. Okay, but getting back to a z-score. So one step up is a z-score of 1. So a z-score here. So if they ask you what's the z-score of 110, well, that's 1 just by understanding. But we do have a formula. So the way you get that 1, the formula. So look, everything in z-scores that's positive is above average and negative is below average, and 0 is exactly average. Okay, so the way you calculate a z-score, if it doesn't happen to fall right on top of one of those, is you take the actual score minus the average and then divide it by the standard deviation. So if they say, what's the z-score of 130, you can just look, because that's on one of the steps. It's 3. If they say, what is the z-score of 125, okay, see, we can't look. We have to actually calculate that one in there. And it's not going to be exactly halfway between 2 and 3. So we have to do the formula then. So the z-score is the score minus the average divided by the standard deviation, which here is 10. So 125 minus 110 is 15. That doesn't seem right. Oh, the average was 100. So that's 25. 25 divided by 10 is 2.5. Okay, so that's how you can calculate. And I guess it is exactly halfway between the 2 and the 3, the 125. Okay, so one more. If they ask you for a z-score of, let's say, 88, okay, see, that's going to be right in here somewhere, so it's going to be negative. So the z-score is your score minus the average divided by the standard deviation. So that's going to be negative 12 divided by 10, which is negative 1.2. So see, there's negative 1.2, and it's also 88. That's how it all goes together. That's what a z-score is. Okay, number 1. Following data, draw a stem and leaf plot. Okay, so stem and leaf plots, what you generally do is like pick a number to be the stem. So like the smallest one here looks like to me is 45. So I think I'll make this the stem. 4, this will be all the 40s, then we'll do all the 50s, 60s, 70s, 80s, 90s, 100s, and 110s, and 120s. Hundred tens will be represented as 11 and a 12. Okay, Now you put them in order. So there, oh, there's a 40. So there's 40. So that means 40. This is the leaf part. Okay, so I did the 40, and then there's a 45. So you just put the 5 there, and then there's a 46. So that, see, that means 46, and then the 7, 47. Looks like that's all the 40s. So I'm going to go through and find 50s. There's a 52 and a 56. So we say 52 and 56. The 60s, I see 63. So that's 63. That's it. Then we go 70s. And you put these numbers over here in order, smallest to highest. So I got a 0, 3, 3, 0, 1, 3, and 3. So there's all the 70s. Oh, there's another one, 78. Oh, there was another 60 right there. So 61 and 63. All right, 80s. There's one. So it looks like we've got 85 and 89. 90s. So 91, 3, 6, and 9. 91, 93, 96, and 99. Hundreds. 103, 109, 109, 108. So we have 103, we have 108, we have 109 and 109. 110, 110, 111, 118. So I have 110, 110, 111, and 118. And then here's the last ones, 125, 125, and 126. That's called a stem and leaf. So we could, sometimes you can see now if it's normal or uniform. It's sort of uniform. So let's draw a stem and leaf plot. What is the 5-number summary? Okay, so you just put that in your calculator. What's the range? So actually we can get the let me just put it in the calculator here real quick. So we got 40, 45, 46, 47, 52, 56, 61, 63, 70, 71, 73, 73, 78, 80, no, 85, 89, 91, 93, 96, 99, 103, 108, 109, 109, 110, 110, 111, 118, 125, 125, 126. Okay. So we can just go to stat, calculate one variable stats. Yours looks just a hair different, but it's basically the same thing. Okay, so there's all the answers to that thing that they're going to ask. So see, there's the 5-number summary. So the range is going to be from the minimum to the maximum. So 126 minus 40. So the range low to high is 86. Whatever the 1-number summary was. 5 number summary, 40, 63, 90, 109, and 126. The interquartile range. See, that's Q1 and that's Q3. They want to know that range. The inside quartile range. So 109 minus 63. Okay, so 109 minus 63 is 46. Okay, so draw a box plot. So I gotta have class right now, so I'll do some more of it at lunch.